You are tuned into AI Paper Slop. Today we are unpacking MemoryWAM efficient world action modeling with persistent memory. And look, if you are building robotic foundation models, you are intimately familiar with the memory efficiency trade-off. Sliding window memory is fast, big O of 1, but it completely fails at non-Markovian tasks where you need to remember past states.
Right, because those states are not visible anymore.
Exactly, and full history KV caching fixes that by remembering everything, but it scales linearly, big O of n. So your latency and GPU memory requirements just absolutely explode.
Which freezes your robot in place.
Yeah, but MemoryWAM solves this bottleneck with a human-inspired hybrid memory. It combines a short-term sliding window, event boundary anchor frames, and highly compressed gist tokens for long-range history.
And that drops the inference complexity from big O of n down to big O of n over d, where d is a compression ratio of 15.
Which is massive. And the results are wild. It hits an 83% average success rate on RM bench, utterly crushing standard vision language action models like Pi 0.5, which sat at a dismal 10.4%.
Yeah, a massive gap.
And it does all this while maintaining low enough latency to operate real-world dual-arm robots in real time.
That latency trap you just highlighted, I mean, that is the exact reason open-world robotic manipulation is hitting a brick wall right now.
Totally.
We're finally moving away from, sterile laboratory desks where every object is perfectly centered in the camera. The real physical world is non-Markovian.
Meaning you cannot fully understand the environment just by looking at the present moment?
Right. But most current VLAs, like Pi 0.5, and even efficient world action models like FastWAM, they operate on a tightly bounded temporal window.
They just map really recent observations directly to action?
Exactly. So if your prompt is, pick up the red block in front of you, a sliding window works flawlessly because the block is right there.
But the second you say, pick up the block I showed you 10 seconds ago before I hit it behind the mug, the system just breaks down.
It shatters. That crucial state information has fallen outside the current observation window.
I mean, trying to do complex manipulation with a sliding window is, well, it is like trying to cook a complex recipe while only remembering the last 4 seconds of your life.
That is a great way to put it.
You look at the stove, you look at the counter, and you just have no idea if you already salted the pasta water. You have basically got anterograde amnesia.
Yeah, and the traditional brute force engineering fix for that amnesia is the autoregressive full history model, something like Lingbot VA.
Where you do not compress anything.
Right, zero compression.
Yeah.
You just cache every past observation into your transformer KV cache. But, to borrow your kitchen analogy, that is like carrying an entire filing cabinet of 4K video around your kitchen.
Oh, wow.
And you have to manually review every single frame before you decide to chop an onion. The KV cache just gets so massive that inference slows down to a crawl.
Wait, I want to pause on a crucial architectural distinction before we get into the memory fix itself. Why are we focusing on world action models, WAMs, instead of just engineering better context windows for standard VLAs?
It really fundamentally comes down to how these architectures handle physical dynamics. Most VLA approaches are purely policy-centric.
Right.
They are just trying to learn a direct mathematical mapping from observation A to action B. So physics, gravity, momentum, object permanence, friction, those are only implicitly learned from the training data.
They do not actually model the world.
Exactly. But WAMs take a dynamic-centric approach. They jointly model visual foresight and action prediction.
So a WAM treats physical dynamics as a first-class modeling target.
Yes, it explicitly learns how the world evolves visually in conjunction with the robot physical actions.
Or better.
But to model dynamics accurately over time, you inherently need history.
You need a timeline to see how things change.
Right, which makes memory the fundamental, inescapable bottleneck for any WAM.
Okay, so keeping all the data is computationally fatal for latency, but throwing it away makes the robot dangerously amnesiac.
Yeah, you're stuck between a rock and a hard place.
So MemoryWAM tackles this by looking at cognitive psychology, which I found fascinating. They essentially built a hybrid system that mimics human memory structures.
Because human memory is not just a monolithic hard drive.
Exactly. Everything is not stored with equal fidelity. It is highly compartmentalized based on utility. And MemoryWAM implements this through 3 distinct pillars of KV cache retention.
And the first pillar is short-term memory.
Right, which is just a sliding window of the 4 most recent high-fidelity video frames. And this is completely dedicated to immediate closed-loop control.
Which makes perfect sense for robotics. I mean, if your end effector is physically gripping a delicate object, you need exact, high-resolution spatial data right this very millisecond.
Yeah, you need the context states, the object motion. You cannot afford to compress the spatial reality of a glass you are actively holding.
No, absolutely not. But 4 frames of short-term memory will not help you remember the original instructions.
Or what the room looked like before you started moving stuff.
Right, which brings us to the second pillar, event boundary memory. In human experience, event boundaries, like walking into a new room, they are highly salient.
They anchor our memories.
Exactly. So MemoryWAM preserves anchor frames to mimic this. Specifically, the 2 initial frames at the exact onset of the task are preserved in full high fidelity.
So they ground the original layout and the instruction.
Yes, ensuring that foundational context is never lost, even if things get severely occluded by the robot arms later on.
Okay, so we have the first 2 anchor frames and the last 4 sliding window frames, all in perfect high fidelity. But if a task takes 2 minutes, there's a massive gap of history in the middle.
And that is where the third pillar comes in. The core innovation of the paper, gist memory.
The long-term compressor.
Exactly. So every single frame in this architecture is originally represented by 120 latent visual tokens. But MemoryWAM summarizes each of those historical frames using just 8 learnable gist tokens.
Which gives us that massive compression ratio of 15.
Yep.
The 120 tokens divided by the 8 gist tokens.
Right. And as the robot operates, the full 120 token KV cache for those older middle frames is entirely evicted from the GPU.
Just totally dumped to save VRAM.
Yep. Only the 8 gist tokens per frame are kept in the long-term cache.
Okay, wait, I need to push back on the actual mechanics of that eviction, though. If we completely clear the KV cache of the old video frames, how do the current action queries actually attend to the past?
What do you mean?
Well, the keys and values they physically need to cross attend to simply do not exist in the memory dinks anymore. They were evicted.
Ah, okay, so look closely at the custom attention mask in Figure 3 of the paper. It is a brilliantly structured matrix. The subsequent video and action tokens do not attend to the old frames directly.
Oh, yeah, they do not.
No, they are hard-coded to only attend to the gist tokens.
Wow. So it is like reading a dense 100-page legal brief, writing a highly concentrated 1-paragraph executive summary, and then just immediately throwing the original brief into an industrial shredder.
That is exactly what it is.
But how do those 8 gist tokens absorb enough mathematical context to faithfully represent a full 120 token frame before the shredder hits?
So before the original high-fidelity frame is evicted, its corresponding gist tokens attend to it, as well as attending to all the historical context up to that exact point in time.
Oh, okay.
During that forward pass, the gist tokens absorb the necessary context, the structural gist of that specific frame. Once that resolves mathematically, the heavy 120 tokens are dropped,
Leaving only the dense 8 gist tokens, so it is a continuous rolling process of summarizing and discarding.
Exactly.
But look, a hybrid memory structure is essentially useless if the underlying brain cannot process it properly. So let us talk about the actual architecture, the mixture of transformers, or MOT.
Yeah, they built this on top of WAN 2.2, the TI2V5B model. Let us unpack the wiring.
The pipeline starts with a causal video VAE, right?
Right, to encode the raw visual observations into compact 48-channel latents. Once you have those latents, you pass them into 2 distinct diffusion transformers, or DITs, working together.
Okay, so a dual branch setup.
Yes. First, you have the video DIT, which sits at about 5 billion parameters. This branch extracts the dynamics-aware features and maintains that hybrid KV cache we just talked about.
And the second branch.
A separate 1 billion parameter action DIT. This branch is tasked with denoising the action tokens while cross-attending to the video KV cache, ultimately predicting chunks of 16 actions at a time.
I have to say, the 3D ropey, the rotary position embedding alignment between these 2 branches is incredibly elegant. Sequence positioning is always such a nightmare in multimodal models.
It really is.
But here, the GIST tokens are placed in the exact same 3D coordinate system as their associated video frames. They pin the width and height dimensions to a constant marker.
Right, and for the Action Expert branch, it shares the video 3D ropey basis entirely. So action queries and cached video keys live in a single, unified positional frame.
So no messy coordinate translations or extra projection layers needed. It just creates a perfectly aligned latent space for visual reasoning and physical control.
Exactly. And moving to the training phase, they train this dual branch MOT using continuous flow matching.
Okay.
But they introduce shifting logic, normal distributions for the noise schedules, and they use radically different shifts for each branch.
What are the numbers?
A shift of 5.0 for the video branch and a much lower shift of just 1.0 for the action branch.
Wait, a shift of 5.0 for video but only 1.0 for action. That feels like a massive imbalance in how the model prioritizes its training capacity. Why skew the noise schedule so heavily toward video generation?
Because predicting how a complex physical scene will visually evolve is a fundamentally higher dimensional, vastly more complex diffusion task than predicting a 14-dimensional action vector for robot joints.
That makes sense. The visual world is just way noisier.
Right. By using a higher shift of 5.0, flow matching allocates significantly more training capacity to the difficult high noise levels for the video branch, forcing it to learn robust macroscopic dynamics.
And the 1.0 shift for the action branch is enough because motor control is a much lower dimensional manifold.
Exactly. There is also a crucial training trick here with the conditioning latents. They linearly mix the clean conditioning latents with Gaussian noise at a uniformly random ratio.
Oh, to prevent the classic teacher forcing problem.
Yep, where the model overfits to perfect data. In standard autoregressive training, the model relies way too heavily on perfectly clean conditioning frames from the dataset.
Right, so by actively injecting Gaussian noise into conditioning latents during training, the policy is forced to learn how to recover.
Exactly. It becomes robust to its own small prediction errors, which is absolutely vital when it runs closed loop in the real world.
And this separation of concerns in the MOT setup creates a staggering inference advantage.
Oh, absolutely.
Because during training, the video branch gives dense, pixel-level supervision for physical dynamics. The model learns physics by being forced to predict the next visual frames.
But during inference, when the robot is actually in your kitchen, you do not have to waste compute generating future video pixels.
Right. You just run the forward pass to extract the deep features, update your hybrid KV cache, and let the action DIT predict the motor movements.
You get the deep intelligence of a video generation model without the crushing latency of rendering output video.
But I can hear ML engineers screaming at their screens right now. They're saying, look, if you want to compress historical data to a big O of one state to fix latency, why not just use test time training or an RNN module?
Right.
Why build this highly complex hybrid attention mask with anchor frames and shredding GIST tokens?
Well, the authors actually anticipated that exact pushback, and they tested it.
They did.
Recurrent neural networks and test time training, or TTT, they are the classic textbook methods for matching a long history into a constant size hidden state. So the paper completely swapped out their hybrid memory architecture for TTT and RNN modules just to objectively measure the difference.
And the results just completely upend the standard efficiency argument. I mean, yes, TTT and RNNs maintain constant inference latency in pure theoretical terms.
Theoretically, yes.
But in practice, they introduce extra network parameters and computationally heavy update operations. The gradient steps required for TTT during active inference are a massive bottleneck.
Yeah, the paper demonstrates that even at sequence lengths of 1,600 frames, both TTT and RNNs were actually slower in terms of single-pass inference latency than the MemoryWAM hybrid memory.
And the latency was bad, but the task performance was the real nail in the coffin. Robotic manipulation requires high-fidelity, targeted retrieval of specific pass states.
Let us look at the press button task in RM bench. It heavily relies on memory to remember a specific sequence of numbers seen earlier. The TTT module scored a 67% success rate. The RNN scored 78%. Full attention, which keeps every historical token, scored 87%.
And the MemoryWAM hybrid memory. It matched full attention perfectly at 87%.
It delivered the full attention intelligence at a fraction of the computational cost.
The reason TTT and RNNs fail so badly here is, well, it is like applying a highly lossy JPEG compression to time itself.
That is exactly what it is doing.
They mash everything into a fixed size, blurred, hidden state. And when you do that, the robot starts to hallucinate, or it just loses the fine-grained visual details it absolutely needs for precise manipulation.
That highlights the fundamental difference between language modeling and robotic manipulation right there.
How so?
Well, in an LLM, summarizing a massive document into a fixed hidden state might work perfectly fine because you generally just need the semantic meaning or the overall tone. But if a robot task requires it to remember, what exact number was written on that specific blue block hiding behind the toaster. An RNN hidden state will inevitably blur that specific visual detail over time as thousands of new frames overwrite it.
But attention mechanisms allow the model to specifically query and retrieve that exact past information.
Exactly. And that makes the big O of N over 15 compression compromise of MemoryWAM the absolute sweet spot. You get the targeted, high-fidelity retrieval benefits of attention, entirely avoiding the linear explosion of full history.
But, simulation charts and arm bench percentages are great for an academic paper, but physical world dynamics are unforgiving. So how does this architecture hold up when a real physical robot is moving its arms in a noisy environment?
They deployed this on an ARX dual-arm robot equipped with a RealSense D455 camera to find it.
And they set up two highly memory-dependent real-world tasks.
The first was the classic shell game, where the robot has to visually track a hidden cube as a human operator rapidly swaps 3 cups around on a table.
A great test of dynamic memory.
And the second was look and press, where the robot observes a sequence of numbers written on a whiteboard and then has to physically press corresponding buttons the correct number of times entirely from memory.
And this brings us right back to the latency trap we discussed in the intro. In the shell game, MemoryWAM achieved an 18 out of 20 success rate.
Very solid.
But the full history model, Lingbot VA, the model that theoretically remembers every single pixel of every single frame perfectly, only managed a 13 out of 20. How does a model with mathematically perfect memory perform worse?
Because control frequency matters in physical robotics. Lingbot VA, massive uncompressed KV cache, makes its inference calculations so incredibly slow that the overarching control frequency of the robot drops severely.
Right.
It takes so long to process the past that it literally misses the camera frames where the human swaps the cups.
Wow.
While it is spending processing cycles thinking about what happened 2 seconds ago, the physical world has already changed in front of it.
It remembers too much to react in time. It is a brilliant irony.
It really is. By significantly reducing the inference latency, MemoryWAM is able to perceive and react to the environment at a much higher frequency, capturing the rapid transient movements of the human operator.
And the ablation studies prove that this compression is not just a clever efficiency trick, it is the load-bearing pillar of the model reasoning.
Yeah, they ran the numbers.
If you strip out the GIST tokens entirely, meaning the robot has 0 long-term memory, the success rate on that press button task craters from 87% down to 5%.
It essentially lobotomizes the robot ability to execute any sequence-based logic.
And conversely, if you remove the sliding window of the 4 recent high-fidelity frames, success on the fine motor cover block's task drops.
Which proves that you absolutely need that raw, uncompressed short-term memory for immediate, fine-grained motor control.
Every single compartment of this hybrid memory, the short-term window, the anchor frames, the GIST tokens, has a mathematically verifiable purpose that collapses if removed.
It is a beautifully engineered system.
It really is. MemoryWAM proves we can efficiently compress continuous, high-dimensional video history into compact GIST tokens and use them for precise, non-Markovian physical control. But look, let us look at the horizon for a second. Video diffusion models, at their core, still inherently lack deep semantic, multi-step logical reasoning.
They understand physics and pixels, but they struggle with complex logic.
Exactly. So if we are now effectively caching the visual gists of the physical world into these dense 8-token representations, how long until we pass those specific GIST tokens directly into a purely logical LLM layer in a dual system architecture?
Oh, wow. That is a fascinating idea.
Right. Are we essentially looking at the localized visual cortex of the next generation of humanoid robots, just waiting to be attached to the prefrontal reasoning cortex of a massive language model?
It definitely feels like that is the next logical step.
Something to mull over as you build your next architecture. That is all for today analysis. Go read the MemoryWAM paper. It is absolutely worth your time. Catch you next time.